Good morning, everyone. Welcome to Options for Entity Interaction. So, I'm going to start like all good talks should. What is the problem we are trying to solve? I've had a lot of conversations with folks about how to implement game mechanics using an entity component system. And I feel that most of the confusion stems from how to get the pieces of your game to interact with one another. There are two problems in particular that I think prove challenging to implement in ECS at first glance. But once you understand those, everything more or less falls into place. The first problem is one where an actor needs to read data from another actor, like when implementing autonomous agents. The follower constantly needs to make sure it's following the new positions that the leader sets each round. This is a read problem. An actor needs to know some information from another part of the game. In contrast, the other major problem is a write problem, where an actor informs another of some information. For example, event systems or triggers. Another example of this would be applying damage to another entity. So, to give us an idea where we're coming from, here's an example of how you might implement a write interaction in the past using game objects. Right? I feel like we've all written code like this at one point or another in our mono behaviors. But this code is deceptively simple. It seems straightforward, but it's carrying some hidden costs. This code makes some pretty significant decisions. Like, for example, now all buttons are capable of being pressed. Likewise, all buttons need to point to some kind of door. And finally, every door needs to have some way of handling being told to open. If you want to modify any of those rules later on, now you have to come back to this piece of code and untangle it from its mess. And don't get me wrong, there are solutions for these problems. You could definitely structure this code better, but I'd hazard a guess all of us have kind of written something like this at some point, not aware of the implications and regretted it later on. This is why object-oriented code winds up resulting in these tangled messes, because we're abstracting away so many decisions that by the time you realize you needed to make a different one, you've already created a huge pile of work for yourself. The truth is, interactions don't really exist. They're hiding the implementation of an underlying relationship. What is a relationship? A relationship is when the value of some data A depends on the value of some other data B. Whenever you write an interaction, this object-oriented way of writing code, you implicitly write a relationship. You are also likely to introduce unintended rules about that relationship. So for some examples of what a relationship looks like, so here's the earlier follower-leader example I had. In this example, the follower's velocity depends on the leader's relative position. That dependency, it is our relationship, and defining it will get the interaction we intended. Likewise, the button in the door's state depends on the button's state. I'm calling this a write relationship. And the reason why is because it's a relationship where we're writing to some other entity. This is one of the reasons why people struggle when working with the entity component system for the first time. It lends itself really well to writing relationships, but not interactions. We're familiar with writing interactions, but not the implicit relationships defined by those interactions. So, if you can understand how to write a relationship, you'll also be able to implement these interactions. From the perspective of someone playing your game, these actors are totally interacting with one another. It's completely fine that they perceive it that way. What's important is that we write it in a way that's closer to what is actually happening. So, just so we're on the same page, I'm defining a read relationship as when the data we iterate upon is dependent on a read from another entity's component, not the entity we're iterating on. Likewise, I'm defining a write relationship as when the data we are iterating on is used to write the data of another entity's components. These definitions will form the basis of the talk today. So I'd like to apologize. Welcome everyone to my talk, Options for Data Relationships. So why is this important? Why is it important we're discussing these relationships instead of interactions? My goal today is that by the end of this talk, everyone here could prototype a small game using dots. The impact of understanding how to implement these relationships and, by extension, interactions, is that it's the fundamental building block of games. Imagine asteroids. If the bullets didn't hit the asteroids, that would be boring. Dots is built on this idea of a relationship. When you write a system, you are writing a transformation, and that transformation is built out of relationships. But because you wrote the relationship explicitly, not the interaction, you have more control to change parts of your code later on that aren't so strongly woven together. You'll find yourself iterating faster. And when you decide to replace how doors work later on, you don't have to change 30 randomly dependent parts of your code. So, how are we going to solve our problem? In order to implement a relationship, we need to build the system that enforces it. Fundamentally, we're building a transformation. So step one is understanding the data we are transforming. This means identifying what data will be our input, what values of that data could possibly be input to our transformation, and the frequency with which the input data changes. This step enables us to decide what components to use, and it helps us build our transformation. Step two is understanding that transformation. What's the relative cost of our transformation, and what's the frequency with which we apply it? We need this information in order to, step three, pick the right tool for our job. Based on that evidence, we can now choose the right tool. And this is a very important step, because choosing the right tool to solve our problem lets us get the maximum performance out of our hardware, and if we need to revisit our code later on, it's in a much easier state that we can build on top of. So I'm going to anticipate a question here. At what point do I need to start asking these questions? How complex does my problem need to be before I need to identify all that information? And that's a good question. After all, it takes time and energy to develop this kind of understanding of your problem. And if you're implementing a relatively simple system, you might feel like it's more work than necessary. If you'll indulge me, let's talk about music for a moment. So I play the alto saxophone. Before I mastered basic rhythms, I could only memorize the more complex ones. Maybe I could play a few, but without really understanding the core mechanics, I was just memorizing some pattern, not the tools that I needed to play all complex patterns. Practicing those simple skills made me way more effective at playing all of the complex ones. And those same principles apply here. Please see what happens if you take these steps the next time you write a system, or really they apply to a lot more code than just here. Practicing these skills on simple problems that will ensure you use them correctly when you need to apply them to solve a complex problem. Plus, as you practice asking and answering these questions, it'll become second nature. You get really fast at doing this. In the spirit of that idea, and because it's a good segue, let's break down an example of a follower following a leader. So, step one, identify the data. I want to give everyone here a quick chance to think about what components you think would be needed to implement that relationship, where the follower's velocity depends on the leader's relative position. Okay, so if you have your components in your head, I'm going to go over the ones that I think we need to solve this problem and that I'll use to solve this problem. First off, we need the velocity. Fundamentally, it is the thing we are modifying, and we need a way to express it. It's obvious we need to know the position of the leader, but to calculate relative position, we're also going to need to know the position of the follower. And of course, because we need to communicate this information, we will also need a leader component that has an entity on it. What is the entity with the position we want the follower to follow? So, next, once we've identified the data we need, let's talk about the domain of that data. The domain of our transformation is another way of saying what are the possible inputs to our transformation. Understanding what's possible to input helps us reason about our problem and lets us make smart decisions about how we implement the relationship. For example, is there a maximum speed, and would it be an error to go out of bounds here? Technically, The position could be anywhere, but there are probably some bounds of our world we can safely expect no data to fall into. For example, can our follower move in the third dimension, or are they locked to only 2 or even 1 dimensions? Something that's really important for us, is it possible for the leader to have no position component? If it doesn't, we need to know what happens, right? This is something that was implicit in our first example in the game object way, but we need to define it explicitly here, and that's a good thing. Oh, and one more thing you may not have considered. How many followers are there and how many leaders are there? This number may not be a value explicitly, but it's still information we need to make an informed decision. To keep our example simple, let's say we only have a small number of followers and leaders. This is a simple case. So, next, let's identify the frequency at which our data changes. Our velocity changes as frequently as we apply accelerations to it. This is going to depend on your game and how you implement acceleration, but here let's just say once in a while we're actually just modifying the velocity directly. The position's probably going to change constantly from the follower because we have a velocity and we know we're applying it every frame. On the other hand, which entity is the follower's leader will probably not change frequently. Even if it changes every few seconds, that's not very often. Remember, you have more than 60 frames every second. Identifying the frequency with which the leader's position changes, though, is a little different than the follower, right? Because what if the leader is some abstract concept that doesn't move, like a waypoint? In that case, maybe we get rid of the leader component and we just keep track of the position we're heading towards. For the sake of our example, let's assume we profiled our game, figured out what we were trying to implement here, and that our leaders move around a lot. That way, we can all stay on the same page as the original example. And also, by the way, if you're looking to optimize your code later on, getting this kind of specific information about frequency, like profiling and finding the actual real numbers, is a great way to identify possible optimizations. These are some hazy estimates, which are fine for getting a first draft of our system, but if we discover that this relationship is really slow, this is the first area we should look at. Let's talk about what the transformation looks like. So first, for each follower in our scene, that's the transformation. We need to run this over every follower in the scene. And to express this relationship, we're going to want to modify the follower's velocity. So we'll add to it instead of getting it, just setting it directly because we want to accelerate. Now, we want some way to verify that the leader has a position component for this transformation to work at all. Otherwise, there's no point in doing anything, so we'll just leave. And finally, we need to do a little math to calculate the relative position of the leader and accelerate towards it. Of course, this following algorithm is incredibly rudimentary, but it's going to work for the sake of our discussion. In fact, I challenge you, go write a follower transformation with a lot more nuance later. It's a good opportunity to practice this kind of exercise. So, the first question we're going to ask ourselves, what's the cost of this transformation? I'm going to give you a few seconds to think about that and what you'd expect this cost to be. Cost can come in many forms. One thing you might ask yourself is, well, she didn't say what kind of cost, and that's true. Because there are a lot of different things you can consider. What is the performance cost of this? How many milliseconds will it take to run? How much electricity does it take to run this code? How many bytes of memory are you accessing? You might even gauge the time it takes to implement an algorithm, the amount of time it takes a programmer to build and maintain the code. Cost comes in a lot of forms. Consider the ones that you care about. Today, we just care about how long it takes to run this piece of code. And so, the cost is relatively low. We're doing some basic arithmetic, and we're reading from another location in memory, and all of that shouldn't add up to very much. We should expect this to be a cheap operation. But if the cost were high, that's okay. Some algorithms are just expensive. Well, maybe this one shouldn't be expensive, but having an idea of the cost of a single use of the transformation just helps our choice of tool later on when considered against the frequency of running that tool. So if we need to come back to this later, we can profile our algorithm and compare its cost to the rest of the program. And if you do this enough, you'll begin to develop this kind of intuition where you can look at this code and say, it's probably not that expensive. The next question we have to ask ourselves is how frequently this algorithm's running. And we can get really precise about this because we have a lot of information already. The frequency of this algorithm is decided by two factors. One, how many followers exist? You can tell that we care about that because there's the for each in our code. That means the more followers we have, the higher the frequency. Two, how often do we run this algorithm? Let's say we run it once a frame. That's typical for this kind of system. Together, that means the frequency total is once per follower per frame. In 1 second, this code runs 60 or more times for every follower we put in the game. Understanding transformation frequency is probably the largest contributing factor to which tool you're going to choose for implementing that relationship. You don't have a lot of choices in tools, to be honest, but this is going to be the most important thing. So really, this is what you want to think about before you choose your tool. And remember, when your data changes, your problem changes. Say we dramatically increase the number of followers in our scene. Well, now we have to make some more decisions, right? Are we going to run this code every frame? Is this going to change which tool we use? We have a different problem now, and we need to start over. But I'm not going to start over because, So, to recap, to express our transformation, we'll need 3 different components: position, velocity, and the leader. Position and velocity will change frequently. The leader will change infrequently. And our domain is really wide. That means there are a lot of possible inputs to this transformation. As for the transformation itself, it's pretty simple, and it's just some basic arithmetic and memory loading. It happens once a frame per follower. So, let's talk about the first tool I'll be talking about today. Component data from entity. If you take one thing away from this talk today, it should be this section of the talk. This is the API you will use to communicate information between entities. If you take one section away from this talk, it's this one. This tool is really critical to build applications with our entity component system, and it's a shame we don't really cover it early enough. So, before we use component data from entity, we'll need a way to iterate over all of our entities. To implement our transformation, we'll use an iJob for each. It's the best tool for iterating over entities. If you're not familiar with iJob for each, what this code says is run the execute method over every single entity that has a leader component, a position component, and a velocity component. If you have those 3 components, then run our transformation. Also notice that the leader and position variables are read-only. We won't be modifying those. So this is our star. Component data from entity takes in an iComponent data type for its type argument. That's the data that you're going to be accessing using it. In this case, we'll need to read the position of our leader, so we'll use the position component here. We're only reading the data on the leader. We don't write to it, so we have to mark it read-only. Next, we can use component data from entity to check if our leader actually has a position component using the .exists function. If it doesn't, then we can't perform the transformation. I decide to just return here. It's pretty simple. In your own application, maybe you make this an error or you assert on it. And here's how you read using component data from entity. You use it like it's an array, right? You pass in the entity that you want to read the component from, and it will return the component data you wanted to read. Nothing too complicated. And then you use it, right? Implementing the transformation was never actually the complicated part here. The part that I think people struggle with is finding component data from entity and knowing to use it to read information like this. So there you go. So how do you get a component data from entity? Because we have to pass this into our job somehow. You have to do so inside your system update. You can call getComponentDataFromEntity, and that will get you a component data from entity. As a side note, we have to pass in true as the argument to get component data from entity because this is a read-only component data from entity. This is necessary for our safety system to work properly. So you'll get some errors if you don't do this. Component data from entity is powerful because it enables accessing arbitrary component data. It's the building block we use for reading data from other entities. What we do need to be aware of, though, is unless we are thoughtful, it's essentially a random memory access. It's possible the data you access could be in a different section of memory, which winds up being a very expensive read. So think about that when you use this tool. Do you actually need to use the tool? Sometimes the answer is yes, and that's very important to understand, but you should still think about it. So why is this the right tool for our problem? If the work you're doing is low in cost and not overwhelmingly frequent, then component data from entity is a fine tool for solving our problem. We could look into other more complicated options, like building acceleration structures to reduce cache misses and keeping all of our memory closer together. But given how small our problem is today, we just want to build this simple system. This is fine. When it comes to read relationships, where you're reading from another entity, component data from entity is the best tool for the job, almost always. So, what good section would be incomplete without a word of caution about using the thing that I just described? It's also possible to write using component data from entity. You noticed we applied read-only before. It is never possible for our safety system to guarantee your safety when you do so, though. For example, this job will throw an exception. Notice that it has a read-only component data from entity, and it also has that same component type as a parameter. The reason why this will throw an exception by our safety system is because this code could generate a race condition. What if you read from a component data from entity that is pointing to an entity that is the entity you're iterating over in another job, right? That is undefined behavior. It could cause a race condition, and it's just not a good time. But if you know what you're doing, you know that that could never happen, that the entities that you're reading from component data from entity are never the same as the ones you're iterating over with the I job because you marked up the query really well. Then you can use native disable parallel for restriction. This tool will allow you to ignore the safety system and basically puts you in charge of handling your own safety. Likewise, you can also write from component data from entity if you use this attribute instead of using read-only. But if you do so, again, it's impossible for us to ever know if you read or write to the same entity or not. So the ball's in your court. Okay, let's talk about write relationships. Writing is a little trickier than reading, as you might have just noticed, because we need to maintain thread safety, and writes modify the state of our program directly. We'll need a tool to deal with that problem, and if you saw Elora's talk earlier in the week, you might have an idea what's coming. So, here's a refresher real quick. Let's talk about the button, because that was the example of a write problem. Whenever the button changes its state, the door will change its state as well. Essentially, the button activates the door. What components do you need in order to accomplish this? What is the data you need to accomplish this? We'll go over this section faster now that you're familiar with the concepts. First off, we're going to need some state that we can look at to determine if a button has been pressed or not. We'll use an activated tag to represent this. If a button is activated, we know it was somehow pressed. We'll also apply the activated tag to the door to inform it that it is ready to be opened. Components with no data in them, component tags, I designate by putting tag before their name. We also want a tag that makes buttons distinct from doors, because ultimately we want to add tag activated to the door. So I've created here tag repeats signal. This tag could be used in more places than just buttons now, right? This button is just one piece that could use this. I want to do some more advanced signal processing later on. I'm doing something with some sort of red rock, and I want to implement that. So we also need to know the entity that the button points at, its target, because that is where it is sending the signal. And the door has no data on it. The door is no data. It's just an entity, essentially. And that's fine. It will have data once we add the tag activated component. That's what we're trying to accomplish. It'll have its own data, but in the context of this transformation, the door doesn't contribute anything. So, as far as the transformation goes, we're programming a system that repeats an activated signal from one entity into another. Debatably, this is low cost. There's some significant overhead to adding and removing a component, but given that it's the only thing we're doing, I can't say it's a really big performance hit. It also won't affect our memory usage normally, which is nice. The frequency is basically non-existent, right? In a given button's lifetime, only a select few frames is it ever pressed. Games today run at over 60 times a second. And if you press a button once every second, then you have applied this transformation once every 60 frames. And even further, it's incredibly unlikely that multiple buttons are being pressed during the same frame. So we know how low frequency this is. So we're going to use entity command buffers to implement this. If you haven't used an entity command buffer before, it's a structure you can write commands into, like set this component to this value, or add this component to this entity. This buffer stores these commands, and then later on at some point executes all those commands at once. That's a little abstract, so I'll give you an example. So here's our job again, and you'll see it has a new attribute on it. The require component tag attribute allows you to require that a component is present on the entities the job iterates over. The name's a little misleading. You can use any component with the require component tag attribute, but essentially the way to read this job is execute on every entity that has a tag activated, tag repeats signal, and target component. This job also, you'll notice, is a with entity, which means it gives us the entity we're iterating on and an index unique to each job. That's going to be important later. One thing you might notice is I actually didn't mention buttons anywhere here. If we needed to, we could specialize this system to button by using another component tag, but I believe we might use it later on, right? So that means that this can be fairly generic. This is a way to write systems that can be reused across your code base. Okay, so you can also see our entity command buffer. I'm using EntityCommandBuffer.concurrent, a special version of the entity command buffer that works in a multi-threaded context. You can use non-concurrent command buffers with jobs, but then you have to schedule only a single job that runs that system. It's unlikely the system runs an incredible number of entities that we would schedule multiple jobs, but I figured I'd mention it just in case. This is the method to add a command to the ECB. Here, we're saying add this component, type of tag activated, to the entity that we're targeting. And we also have to pass in an index because this is a current entity command buffer. The index is how we guarantee thread safety. We can later on compile these commands in a way that makes sense as opposed to having to, add them all together. So, of course, we need to obtain an entity command buffer. And we're going to talk about how, because the technique is pretty important. Remember how I mentioned that entity command buffers need to playback? That means until playback, the component we added is not actually added. It's really important that our system opens the door after the component has been added. And so I find it really helpful when using entity command buffers to think in terms of the synchronization points that exist in our game. If you're not familiar with it, when we run our systems, we need to decide which group of systems, a system group, we will run those systems in. By default, there are 3 of them: initialization, simulation, and presentation. If we don't specify anything else, every system we write winds up being scheduled in the simulation system group in the middle. And it just so happens we have some special systems called EntityCommandBuffer systems. EntityCommandBuffer playback occurs during these special systems. When we want to use an ECB, we have to get it from one of these systems. And you'll notice here, there is an ECB system at the beginning and the end of every single one of those system groups. But we can make our own. So we're going to create a new special EntityCommandBuffer system that exists somewhere between the other two in the simulation system group. This is because we still want to do the doors simulation before presentation happens, but we need to have a command buffer in the center to make sure everything's synced properly. So if you're wondering where I got this system from, I wrote it myself. How to build one of these systems on your own is out of the scope of this talk. And if you're worried that maybe you can't take advantage of this, it's okay for you to use like the begin simulation command buffer system and those default ones that exist. I'm just also pointing out that you can make your own if you need to. So, create command buffer. You basically just take the system and you call create command buffer on it, and you call .toConcurrent, and you get a concurrent entity command buffer. It's pretty simple. The only other thing we have to do is add the job handle to the system so the system knows not to run until this job is over. Aside from that, it's pretty straightforward. I also want to talk about this one neat trick I discovered, because I haven't seen many people use this yet, and I'm still figuring out if this is a good pattern or not, where it is and where it isn't. But consider this. You could take two command buffer systems, one at the beginning of a simulation group or even a frame, and one at the end of it. And in the same system, you can schedule the add and removal of a component. That means we know exactly the lifetime of that component on that entity. It forces the action to be resolved, and we're confident that it will be removed because we're removing it in the same system we're adding it. Only it's deferred, so it works out, and it exists for some period of time. This isn't always going to be the best tool at your disposal, but it is a tool you have access to. So, why is the entity command buffer the right tool for write relationships? One, we need to perform a state change, and we can only do that within a job using an entity command buffer, so we kind of don't have a choice to begin with. But also, the data we depend on isn't changing frequently, so even though there's a little overhead with using the entity command buffer, we can afford it. We don't mind deferring our work, and we don't need to immediately react to the change of the value. If we did, maybe we would use ComponentDataFromEntity for value relationships, but most of the time it is okay to defer. You just have to think about it in terms of where you're syncing up later on. So in general, entity command buffers are the tool you will usually use for implementing write relationships. So, read relationships versus write relationships. Why would you use one over the other? Oftentimes, a read relationship can be implemented as a write relationship and vice versa. For example, instead of the follower reading the leader's position, the leader could write to the follower's velocity directly. In the case of the button, the door could check the state of the button every frame, and that would turn it into a read relationship instead. But under normal conditions, those implementations would be worse than the ones we chose. And they're also a little less intuitive, but let's talk about why they're actually worse instead of just assuming it because we intuited it. In the case of read relationships, they tend to be very effective when the transformation is frequently applied. This is because reads can happen easily in parallel, but writes often cannot. They force sync points. They force us to go single-threaded for a little bit. As a result, writing the component is going to require us to defer the write or deal with the expense of single-threaded code. When that's frequent, that really hurts. On the other hand, write relationships are really good for infrequent things, like the button, for example, or maybe when a projectile hits a player. right? These happen very rarely in the grand scheme of the program. And so write relationships tend to be very effective because you don't waste time polling for a state change every frame, right? Imagine reading the button's state from the door every single frame and not using it for 99% of frames. That's just a waste. So, as an added bonus, also note that writes give authority to the person, to the actor performing the write. For example, when a projectile hits multiple actors simultaneously, the projectile would like the authority to decide which actor actually gets the damage applied to it. If the actors had to figure that out from a read, they would each have to come to the same conclusion somehow. And that's a little messy and probably more work. Okay, let's recap what we talked about today. Interactions are an object-oriented way to think about what is implicitly a relationship. Relationships are whenever the value of some data depends on the value of another piece of data. And by implementing relationships, we implement the interactions our users experience. You still get the interactions you all came here for today. A read relationship is when the data that we're iterating on is dependent on a read from another entity's components. And a write relationship is when the data we're iterating on is used to write to the data of another entity's components. Which one you use depends on frequency. The steps to implement a relationship, the problem-solving skills we used to solve this problem, were 1, understand the data we're transforming by knowing what the data is, how frequently it changes, and what the possible inputs could be. We need to understand the transformation we're applying by identifying its frequency and cost, because it will be necessary to pick the right tool for our problem, and then we can pick the right tool for our problem. And again, when your data changes, your problem changes. If the frequency of your data changes, then suddenly you have way more followers. You might have to rethink your whole problem. And finally, you have ComponentDataFromEntity and the EntityCommandBuffer. These are your tools for implementing these relationships, for getting entities to communicate information to one another, for building the systems that are fundamental to all games. ComponentDataFromEntity is good for read relationships because it tends to work well in high-frequency environments. But do be careful of the possible extra overhead of reading random memory. And entity command buffers are great for write relationships because they're low frequency. They do require you to defer your work until a sync point, which is a little expensive on its own. There's never a perfect option, but there was never a perfect option before. So these tools will serve you well. Any questions? Okay, so the question was, what happens when, for example, you have to add a lot of components with data to an entity? Because when you do so, for example, AI that maybe needs a lot of information temporarily through components and then can have them removed later, that entity winds up living in another archetype. Does that result in worse performance because now you have to prefetch another area in memory? The answer is, well, yes, if you are moving it to another piece of memory, then that could cause some, that is not fresh cache anymore, especially if there's not a lot there. But think about the frequency with which you're actually doing that, right? Say you have, 20 AI agents, and you do this maybe once a frame. That could be kind of expensive, but it's pretty small scale still, depending on how much data you're moving. If you're moving large amounts of data, maybe you can ask yourself, do I actually need to be adding and removing these components every frame? Maybe I just have one component that is essentially, a Boolean that says, hey, this is on, this is off, right, when to use it. I wouldn't add the components and remove the components every frame unless you needed to, because it does cause these structural changes that can be kind of expensive. And I would find a solution that doesn't involve moving the data around so much. Okay, that's a good question. So the question was, say you have multiple followers following the same leader, and you want to make sure they're not colliding when they enter the same cell and area. And so the way I would go about implementing that is I would think about it in terms of, well, I am changing the position of these followers, and the order in which they move is very important to me. So I would probably make that one single job, not multiple jobs, and that way you can control the order that they wind up in that location. You can still take advantage of multi-threading if you use the schedule single function call, right? You're scheduling one job instead of many jobs, but it can still run concurrently to all the other work in your program. Okay, so the question was, how well do these kinds of tools scale? Especially a concern was that, if you disable type safety like this in a very complex system that touches a lot of pieces of data, how do you handle that? And I think it's a two-step process. The first step is break up the system where you can, right? If this system can actually be composed of different interactions, then having smaller discrete pieces can be valuable if it gives you more control over running these sorts of systems in parallel. The other answer to your question, though, is that the type safety, when we're disabling it on that specific type. We're not disabling it for the entire system as a whole. So it'll only be necessary for the parts you're directly writing with. That works out more or less in your favor. You can totally mix game objects and the entity component system if you'd like as well. But often when you do so, it winds up requiring you to copy a lot of data back and forth between the two. It tends to do well to try to live as much in the entity component system as you can if you can afford to transfer things over. Okay. So the question was, how do I enable interactions between traditional, like monobehavior game objects, and entity component scene parts? Like, for example, how do I have a particle system that is implemented using game objects follow an entity that's moving around? The answer for this is it's okay to use the entity manager in your monobehavior to read the position of the entity every frame. It's expensive that you are doing this more expensive read, but when we're interacting with old parts of Unity, this is the compromise we have to make. That's why entity component system is really effective for the parts of your code you need to get very tight and optimized, and you can still use game objects for other things. I have to go now. My time is up. So if you need to talk to me, I'll be available afterwards, and I will also be at the expert bar for an hour shortly. Thanks.